Okay, good morning, class. Can you guys hear? Can you see the screen?
Yes, sir.
Good morning, sir. Yes.
Great, great. All right, so everyone got their grade back for the previous test, right? The test on angular motion. Yeah.
Yes, sir. Should I use market?
Yeah, me. I think you guys didn't do as well on this test compared to the projectiles one. In the projectiles test, a lot of you got 20, I think, and in this test, you guys didn't do so well.
So I got 15, but I think I get missing the solution via Google. When I check it back, I think I compare and I get the same answer as miss. So I want to get 15.
Chances are you missed the part or you submitted late.
Probably it's
Yeah.
late, but miss the extend the time a little.
Well, the time she sent me to cut off was 9:50, I think. So every minute after that, you lose a mark, right? John
Okay.
Choi is raising his hand. John?
Yes, sir. Yes, sir. For that day on the test, I had sent an email to Miss stating that I was in work and I couldn't have been able to do the test. I didn't get a chance to attempt it, but she never
Okay.
responded, so I never knew what would be the outcome.
All right, let me just make a note of it, right? And we'll sign you up for the reset at the end of the semester because it's gonna do all the resets at the end, just like last semester, instead of having them in between.
Good morning, Mr. Chatterpal.
Yeah.
I just confirm that you make a note of my first receipt.
Yeah,
This is
yeah.
Yannick Barr speaking.
Yeah. Internet issues.
Yes. Yeah, it's Yannick Barrow.
Yeah, I have it here.
All right, thank you, sir.
Yeah, we'll do the resets, all of them, at the end of the semester. All right, good. Yeah. Some students were complaining that you guys didn't have enough time. Miss gave you guys very little bit time for the test.
Yes, sir. The test was very stiff.
Yes, sir. Yeah, we had any time.
Yeah. Okay, well, it's your second semester. You're no longer in first semester, so you're stronger now, right? You're smarter. You learn a little bit more adaptable now, right? So, gotta come prepared, right? Practice a lot. Become really fast at working these questions, so that even if Miss give you 5 minutes, you're ready, right? All right, good. So today we're gonna continue on collisions. Is someone saying something?
Sir, we got plenty people who in unmute or unmute themselves.
Maybe you just mute everyone. All right. Okay, good. So today we're going to continue on with collisions, focusing more so on impulse and momentum, right? So we're going to do two questions that are similar to what we've been doing before, right? With trucks and stuff colliding. And we're going to do some that are slightly different. And we're going to pay a bit more attention to the kinetic energy loss and kinetic energy before and after impact. Because last class, we just kind of dismissed them as being perfectly elastic sphere, so therefore no kinetic energy is lost. And I think I gave you guys to find the kinetic energy lost for one of them, right? Okay. So let's just start with number 4. A pile driver, mass 1.5 tons, falls freely through a distance of 2 meters on the pile, right? Pile driver falls on the pile. The pile's mass is 0.5 ton. When the pile is nearly fully driven, the average resistance is 800 kilonewtons. Determine the penetration at this stage and the kinetic energy lost at impact. Okay, so a few things. we know since the topic is impulse and momentum, we might need to find momentum of the pile driver to see what happens when it hits this stationary pile, right? So the distance traveled is 2 meters. It falls freely. Now is a pile driver. Let's just pretend it's smaller than a square. And it falls freely for 2 meters, right? 2 meters. Now, what force acts on it? Well, gravity acts on it, inducing that acceleration due to gravity, which is 9.81. Now, what we have here is a distance and some acceleration, right? Now, we know the formula that relates distance and acceleration to velocity, which is what we want to find momentum, right? Momentum is equal to that mass times that velocity. So we want to find this velocity. And the formula we know that equates these two is that v squared is equal to u squared plus 2s. Now, alternatively, you might have seen this formula here, v is equal to the root 2gh. But these two are actually the same. Let's consider that the initial velocity is 0, right? The acceleration, of course, is g, and the distance traveled is that height, 2, right? Let's call it h. Transposing this formula, we get v squared is equal to 2gh, and you carry over the square root, right?
Sir.
Root both sides, then you get root 2gh. Okay, some people are raising their hands.
Yes, sir. I was just wondering if the pile is being propelled or a force.
Like some
with
force is being added to the pile driver?
Yes.
No, well, according to the question, it falls freely.
No,
Right,
I understand that. I was just asking if that happens, what you do.
You add it on to, well, you're gonna have to add it on some way. You're gonna have to work backwards, I guess. Force, mass times acceleration. I guess add that on to, well, you'd have to guess, that would increase the acceleration. So you'd have to find like average acceleration. And then you find velocity based on that, because there'll be acceleration due to gravity, right? Acceleration due to gravity and acceleration from your force, right? If it's a continuous force, like F is equal to MA, it's a continuous force, right? That force is going to continuously accelerate that body, right? If it's a short force or an impulse, right? Impulse, right? It's going to accelerate it a little bit for some short period of time, right? Okay. But this question doesn't answer that. And we'll cover that. I think there might be questions that cover that as we go forward, but this is just generally how you would do it, right? You need to factor in that additional acceleration based on that force. And of course, it depends how long is that force applied, right? Is that force being applied continuously or just for a short period of time, right? And use your equations, relate, right? Make sure you don't break any rules of mathematics, and you should get along fine. All right, so as I was saying, these two equations relate, essentially the same thing. So using that, we can find velocity. Velocity of the pile driver, striking velocity, or velocity just before impact, velocity at impact, something like that. V is equal to square root 2 times 9.81 times 2 meters. It's falling freely. So gravity. Plug this into a calculator. You're going to get V is equal to 6.264 meters per second. Okay? Meters per second. And that's your striking velocity. Now, knowing this velocity, we can now say, what's the momentum of the pile driver before impact? The weight of the pile driver is 1.5 tons, right? Tons. 1.5 tons is 1,500 kilograms, right? Multiplying the two, the velocity, 6.264 and 1,500 kilograms, we get the momentum of the pile driver before impact is equal to 9,396 kilogram meters per second, right? Kilogram meters per second. Now, the momentum of the pile before impact, remember, the pile driver is coming down, right? Coming down, hitting the pile, right? The pile is stationary, right? So it's going to be 0 meters per second times the weight of the pile times the mass of the pile, which is half ton, 500 kilograms, which is just 0 kg meters per second, right? 0 kg. Now, just like the previous questions, right? Just like the two trucks crashing together and sticking, right? This pile driver is going to come, hit this pile, then they're going to join together, and the same momentum is going to continue driving the pile down, right? They're going to come, they're going to stick together, and this pile driver is going to drive that pile down. So the velocity is going to be a common velocity of this and this, right? So the two trucks, truck A and truck B, right? Truck A and truck B, they crash together and then they become one body, right? A plus B. And they travel at a common velocity, right? Okay. Now, how do we calculate that common velocity? We say momentum is conserved. So the momentum before is equal to the momentum after. And because this is a combined body, truck A plus truck B, or pile plus pile driver, we add the weights up, right? And multiply that by this common velocity, which we can denote as some symbol V, because it's an unknown, and that's what we would like to find. Right, so some common symbol V plus the weight of both of them, right? Truck A plus truck B, pile plus pile driver. Pile is 1.5 tons. Pile driver is 1.5 tons plus pile, which is half ton. This is equal to 2 tons or 2,000 kilograms. Okay, 2 tons or 2,000 kilograms. So good. Now the momentum before is, of course, momentum of pile separately plus momentum of pile driver separately plus momentum of pile is equal to that 2,000 V. Solving for V, we have V is equal to 9,396 divided by 2,000. Therefore, V, the common velocity, is equal to 4.698 meters per second. And that's the common velocity. What else does the question ask? Okay, determine the penetration at this stage and the kinetic energy lost at impact. So penetration, okay? Penetration is similar to distance traveled, right? We know that energy used / work done is equal to some force times some distance traveled. And that's the same as penetration. So what we can do is find the kinetic energy being used in this system, right? And equate that to some force times some distance traveled, and then solve for that distance traveled. That force is going to be 800 kilonewtons, right? As the resistance, the average resistance. So it's going to be work done. Work done is going to be that 800 kilonewtons times some distance traveled, right? Travel. Okay? And this, of course, is all going to be equal to the energy used, right? The energy used within that system to overcome this resistance, right? Okay, good. Now, kinetic energy after impact. So the common velocity is, of course, velocity after impact, right? V prime, velocity after impact. So the kinetic energy after impact is half mv squared. Half mv squared. The mass is that common mass because, of course, they stuck together now and they move as one. So it's that same 2,000 kilograms. So half of 2,000 kilograms times v squared, which is what we just found as 4.698. We square that. So the kinetic energy after impact is equal to 22,071.204 or 22.071 kilojoules, right? You can always just use kilojoules instead of writing like a very large number. Okay. Now we know this kinetic energy here should be related to that work done. Now there's also something else you guys need to take into consideration, right? That there's some loss in potential energy as well. Because not only is the pile driver hitting the pile with some sort of force, right? Causing that little loss on impact, right? Loss on impact, and then a transfer of kinetic energy, right? Transfer of kinetic energy. And then it's in turn just moving the whole body, right? The entire body is moving based on that kinetic energy. There's also another force acting here, and that force is gravity. Gravity is helping to pull the entire body down. Therefore, we need to factor in the weight, right? So 2,000 kgs times the force per kg, which is newtons per kilogram, which is 9.81 newtons per kilogram, right? And that there works for some distance, which is a distance traveled, right? There's also potential energy that we need to take into consideration that is expended or converted to kinetic energy as we move through the ground. Okay, good. So the loss in kinetic energy, all the kinetic energy is going to be spent up, plus some additional energy that comes from gravity, right? Adding those up, we say the kinetic energy after impact that we used up to travel the distance, right, is 22,071 joules plus the 2,000 times the 9.81 times distance is equal to 800 kilonewtons times distance, right? This is the work done. Is the work done. Now what we need to do is carry over, factor out distance, and then divide by that. Okay, so we're going to carry this on the other side. and it's going to become minus 2,000 times 9.81 times distance on distance d. Okay, we can multiply this out. 2,000 times 9.81. 2,000 times 9.81. And of course, we're going to get newtons, right? 19,620 newtons. We can divide it by 1,000, and then we'll get kilonewtons, right? Kilonewtons times, of course, is distance. Let me erase that. That becomes 19.620 kilonewtons, just like here, times distance. Factor out the distance, we get 800 kilonewtons minus 19.62 kilonewtons times distance. So to find distance, we carry this over back, this entire bracket here that's multiplying, right? Divide both sides by that. We end up with distance is equal to 22,071 divided by this 800 minus 19.620. Minus 19.620. Plugging this into a calculator, we get 28.28 millimeters, or approximately 28.3 millimeters. Millimeters is because we use kilonewtons, right? Use kilonewtons. Okay, if we use newtons, we would have gotten our answer in meters, all right? Good. Now, I noticed in Mrs. Sills working from the solution, she didn't factor in this loss in potential energy, right? It's here. And she got an answer, something like 27 point something, right? But I saw the book had this answer, so it's possible that she just forgot to factor in this loss in PE, right? Okay, good. So any questions on this? Slightly different way to solve it.
Like when in this so I do the same thing that you do, and I change the kilonewtons to newtons, and again 0.027589, or you'll be 27.589 meters.
589.
When I convert the kilonewtons to newtons, and then solve it.
So when this is going to be 27.5 something. So chances are 5.8. So chances are you just made some small errors when you round off this piece, and maybe just rounding up some places, right? Cause you to get a slightly different answer. It's just the decimal places, right? This here you multiplied by 1,000. Wait, what did you get? Meters. Yeah, you multiply by 1,000 means you get 27.58, which is close enough to this. But check, make sure you didn't make any small errors along the way. Okay, any other questions? Yannick, go ahead.
Mr. Pratt, I asked her to explain the rationale from the last kinetic energy plus the last potential energy equal to the work done. Just run it through. I think I missed something.
So remember, energy is what we use to do work, right? So in order to do work, we need to spend energy, right? We need to spend energy to do work. So the amount of energy we lose, loss of energy, should be equal to work, right? Because they have transferable units and essentially relate to the same thing, is just at different times. Energy is before we do work, and work came about as a result. But numerically, quantifiably, they're the same thing, right? It's just that energy is before and work is after, right? Timing wise. It's like saying,
Sir.
Yeah.
I was just saying that she used the kinetic energy after impact.
Alone, right?
Right, and that is equal to
Yeah.
work done. And when I did it, I got 27.59.
Yeah, so did you look at the handout? I'll come back to your question, Yannick Barrow. So I'm saying she just probably made a mistake and forgot to factor that in.
No, but when you're doing it there, you're using loss in kinetic energy.
Yeah, which is the same as the kinetic energy after impact, right? Because all of this energy is used to send the pile down, right? So this here, and this here, right? This is the same 22,000 is the same 22,000. Yeah.
The loss in kinetic energy is 7.359.
No, not loss in kinetic energy after impact, not lost in kinetic energy during, not lost kinetic energy lost at impact, loss in kinetic energy while driving the pile.
Okay.
Yeah, this is energy, kinetic energy lost at impact, right? At impact, this is loss in kinetic energy while driving the pile, right? I can change this in the handout to avoid confusion, right? This is loss kinetic energy that we use up to drive the pile down, right?
Okay.
Yeah, loss in kinetic energy. This is kinetic energy loss at impact. I can change this to, I can change it to KE at impact. I can change it before I send it out. All right, so what I was saying is that Miss used this alone, but the book
She also said the book had some wrong answers.
Yeah, but it's just that the book, it does have a wrong answer somewhere, but this here is 28.3 millimeters, right? Which is the same answer I got here, right? 28.3 millimeters, right? So I guess she just forgot to factor in a loss in PE. Okay. And I think the book worked the example without the loss in PE. So it's just, I guess, a matter of how you do it. So 28.3 millimeters. All right. 28.3 millimeters. If you guys want to work in this way, during the test, if a question like this comes, I'll mark both as right. But if just know that if you want to get the same answers as what the book has, this is how you do it, right? You need to factor in that loss in PE. And when you think about it, gravity does play a role, right? It's not just the speeding up and hitting the pile. Gravity also assists. Gravity is also still acting on this body, pulling the pile down, right? So you need to take that into consideration. Okay, good. Great. So everyone's fine with this answer. And I was explaining back to Yannick Barrow. All right, so the loss of energy is equal to work, right? Loss of energy is equal to work, as I was saying, because this is like before we use up, the energy is like before we use it, and work is after we use it, right? The work done and energy, right? The energy lost should be equal to that work done, right? Because we use energy to do work. So these two should be equal. The work done is force times distance. And this here is just in joules. The unit should work out because of course in Newton is just some kg meters per second squared some stuff. So all the units should work out and they should be the same. Yeah, Yannick, you kind of understand it now?
Understood clearly now, sir.
Yeah, because it's just energy. We use the energy to do work,
Yeah.
right? It's the same thing. Okay, good. So now I want you guys work this part, which is the kinetic energy lost at impact, right? Not the kinetic energy loss, but not the loss in kinetic energy while driving the pile. But the loss at impact, right? Two different times within the system. Energy is being used and gathered all throughout the system. But what's the energy lost at impact, right? At impact, when you see things strike each other. Okay, good. So you guys can go ahead and calculate this. How you calculate this? We know kinetic energy is equal to half mv squared. We have the kinetic energy after impact. But what is the kinetic energy before impact? Well, that comes from the pile, and the pile is 1500 kg, and the velocity of that pile, we know the velocity of that pile as 6.264, right? Alternatively, you can use potential energy, which is mgh, all right? This is mgh. And then subtract the two, and you should get the loss in kinetic energy. So take a few minutes and do this. And tell me if you get the same answer.
Yeah. Mr. Chatterpal?
Yeah.
Anthony most
Yeah.
like, sir.
Yeah, the person get overbearing now, the individual.
Yeah, what were you saying, Yannick?
No, I was just saying, yeah, the individual, the mic on, getting overbearing now.
Oh, I muted him.
Mhm.
So remember, guys, go ahead and calculate this, right? Kinetic energy loss at impact. Did you guys get this answer? 7.359.
Yes, sir.
Did anyone not get it? Needs help? Wants me to go over the formula again?
Sorry, you could just go over the formula, please.
So, yeah. So remember, kinetic energy after impact is this 22,000, right? 22.071 kilojoules. Let's just call it kilojoules, right? And the kinetic energy before impact, remember the pile isn't moving, but the pile driver is moving at a velocity of 6.264. So we use that 6.264 with half mv squared. 6.264 is here. Mass is 1.5 ton, which is 1,500 kilograms. Calculate that, subtract the two, right? And we should get 7.359 kilojoules, right? Alternatively, right? If you don't want to do this, you can use mgh, which is mass times gravity times height, which is 2 meters, right? And then subtract the two, right? Alternatively, mgh. Okay, remember the mass is 1,500. Okay, all right, take another 2 minutes, do it. Tell me when you get the answer.
Sir?
Yeah, you got it?
Sir, I have a question. Well, what are you subtracting to get the loss in potential energy?
The two, kinetic energy after impact and kinetic energy before impact.
No, the loss in potential energy.
Oh, you're not subtracting anything, right? Because the potential energy is energy that comes about as a result of gravity, right? So this new body weighs 2,000 kilograms and force per kilogram, gravitational constant, is equal to 9.81, right? And that is being used across a distance of that same distance traveled, right? So it's kind of like pretending there is some box, right, at some height, the same MGH, right, the same MGH, and it's about to fall some distance, right? Some distance h. Some distance h. But instead of falling freely, there's a force resisting it, right? There's some force resisting it. So it doesn't fall freely, but it still has that same potential energy, right? Potential energy, it still has the same potential energy, but instead of falling freely, there's this 800 kilonewton force disrupting it, right? Acting against it. Yeah. So you're not subtracting anything. You're just saying that it has potential energy being the combined mass of that 1.5 tons plus the half ton, which is 2,000 times 9.81, right? It's weight, it's force as a result of gravity acting downwards. So gravity adds potential energy into the system, and that potential energy, as we drive the pile through, is converted to kinetic energy, drives the pile, and is lost. It's lost because it's doing work. It's doing work driving the pile. Okay, does that make sense?
Yes, sir.
Okay, see, you're not subtracting anything. It's just additional energy in the system from gravity. Because gravity is acting on the system, and we need to factor that in. Okay, did everyone get this 7.359 now? The guy that asked me to explain the
Yes,
form on
sir.
the back. Yeah, as well?
Yes, sir. Yes, sir.
Okay, good. Moving on. Number 5. Yeah, number 5. A block of wood of mass 23 kg is suspended by a cord. A bullet of mass 23 grams is fired into the block with horizontal velocity of 500 meters per second. Calculate the common velocity after impact, the loss of energy at impact, and the height of which the block rises above its original position. Okay, now first things first, momentum of bullet before impact. The bullet strikes some block, is hanging by a cord. Now this is stationary, and this travels at some speed of 500 meters per second, right? So this has momentum, this has no momentum, right? Momentum of bullet before impact is its mass, 23 grams, convert to kilograms, we get 0.023 kilograms. Times that by its velocity, which is 500 meters per second, we should get the momentum of the bullet before impact is equal to 11.5 kilogram meters per second. The momentum of the block before impact is obviously 0, multiplying its weight by its velocity, which is 0. Good. Considering, again, as usual, that momentum is conserved, we get 11.5 kg meters per second plus 0 is equal to 23.023 V. V here is again common velocity, because the bullet, let me draw this back, okay? The bullet strikes the block and is embedded in it, and it moves the block this way. The block is hanging on some rope, some cord, right? So V, common velocity. They're not elastic, they don't bounce away, they don't bounce apart or anything like that, right? They remain stuck together. 23.023, of course, comes from the weight of the block, which is 23 kilograms plus 23 grams, which is 23, plus 0.023, which is equal to 23.023 kilograms, right? Good. So with that, we end up V is equal to 11.5 divided by 23.023. Therefore, V is equal to 0.4995 meters per second. Meters per second, or approximately 0.5 meters per second. Okay, now we can use this to find the kinetic energy before impact and after impact, and then subtract them to find energy lost at impact, right? So common velocity, we've just found that as being 0.5 meters per second. The loss in energy, of course, energy before, energy after, subtract, we get loss of energy at impact. Okay? So we can do either one first. Kinetic energy after impact, we use the same velocity, right? Half mv squared. The mass is of the collective body because they move together, and the velocity is the common velocity, velocity of the collective body, right? Because they move together. Plugging this into a calculator, right? We should get kinetic energy after impact is equal to 2.877 joules. Very small, 2.877 joules, right? Now, the kinetic energy before impact comes from the bullet alone, right? The bullet's velocity is 500 meters per second. The bullet's weight is 0.023 kilograms or 23 grams, right? Remember, the block isn't moving, the bullet is moving and being fired into that stationary block. Plug this into a calculator, you will get the kinetic energy before impact, which comes from solely the bullet, is equal to 2,875 joules, right? Joules. Now, what we notice is that kinetic energy after impact is 2.877 joules, and kinetic energy before impact is 2,875 joules. Therefore, a lot of energy was lost. The reason for that is that the bullet is very small. The bullet is very small, and the block is very big. So upon hitting this block, the bullet and its energy, a lot of energy within the system is lost just because this bullet is very small and this block is very big, right? Causes all the energy to dissipate, right? Because it has to move this giant block. So a lot of energy is lost. How much energy is lost is, of course, the difference between those two, right? So we subtract or 2,875 from a 2.877. And we say the kinetic energy loss is 2,872 joules or 2.872 kilojoules, right? Now notice this is very close to this because almost all the kinetic energy is lost. Okay. Now with the kinetic energy remaining, the kinetic energy after impact, the kinetic energy remaining, this is what's used to do the work of moving the block, right? So this is what we're going to equate the work done and find that height. So we just found common velocity, which is up here. We use that to find kinetic energy loss. Now we're going to use the kinetic energy after impact, kinetic energy remaining to find the work done, which will lead us to finding height. All right, good. Now the loss in KE, right? The kinetic energy used. I should start changing this to kinetic energy used or kinetic energy after impact in order to not confuse you guys, is equal to the work done. Okay, good. So that 2.877 joules is equal to mass times gravity by distance. Now the block, of course, has some force to be overcome. In order to move this block up some height, because it's swinging on some cord and you're shooting it, in order to move it, you need to overcome gravity, which is overcome its weight, right? That's the force, pulling it back down, right? Some force pulling it back down, and that's mass by gravity. Now, also, remember the bullet, the 0.023, comes and it's embedded into it, transfer some of its kinetic energy, and now it's a part of the block, right? So we also need to move the weight of the bullet plus the block, right? Which is 23.023 times 9.81 times some distance. And this is the work done. Now the kinetic energy, the loss in kinetic energy is equal to the work done. Simplifying this, we get 2.877 divided by this, right, is equal to distance. So we get distance is equal to 2.877 divided by 23.023 times 9.81. Plug this into a calculator. You should get 0.01274 meters or 12.7 millimeters. Okay, if this was kilojoules, you would get meters right away. You would get millimeters right away. Okay, now what you guys must be thinking is, why isn't there a loss in PE? Well, notice before with the pile, right? Pile and pile driver, they were moving downwards, right? Downwards. Moving downwards with gravity. In this case, this thing is moving upwards. Let me just plug in my charger. Right. Just give me a second. Okay, I'm back. So as I was saying, there is no loss in PE because in the case of the pile and pile driver, they were moving downwards with gravity. this system is moving upwards or sideways and upwards because a bullet touches some block, a bullet being shot in some block, at some cord, which is going to move sideways and then eventually upwards, right? Now, the force that they're resisting is gravity. So gravity is on this side of the equation, which is the resisting force. It's not adding force into the system to help it move. We're moving against gravity, right? So that's why there is no loss in potential energy, because there is no additional potential energy helping to do work. All right, good. So keeping that in mind, loss in KE, or kinetic energy used, is equal to work done. Put our values in, or mass or gravity, which is the resistance. Our kinetic energy used is the kinetic energy that's left in the system after impact, right? The distance traveled is the height, which is what we want to find. Solving for distance is equal to 2.877 divided by the 23.023 times 9.81. Then we multiply by 1,000 and we end up with 12.7 millimeters. Any questions on this?
None from me, sir.
Anyone else? No. Now, the only difference is that we didn't use we didn't use PE here. We just used KE because we're not moving with gravity, right? Gravity isn't helping us do work.
Thank you. That's a good question for 30 seconds. This is it.
That's good.
Yes, sir.
Good. All right. And for this one, I think Mr. Sell worked it the same way and the book has the same answer, I think. All right, good. So number 6. We did this question before in the last class with 2 trucks, but instead this time now it's a truck and a stationary truck. So what I want you guys to do is go ahead, follow the same principles and solve this question, right? Common velocity, loss in KE, pretty similar to what we did in last class. So let me just read it and then I'll give you guys maybe 7 or 10 minutes to work this question. All right, good. So number 6, state the third law of motion and illustrated by an example. You guys can ignore that or you can do it if you want, okay? A 20-ton truck moving at 14.4 kilometers per hour collides with a stationary 10-ton truck. And the two move on together, right? Together. Calculate the common velocity and the loss of kinetic energy due to impact. So take a few minutes and do it and tell me whether or not you get these same answers. Okay, then we'll move on to number 7.
So we get 2.67 meters per second and 53.07 kilojoules.
So you meet it if you're talking.
Hello, I was muted, right? Sorry about that. Yeah, so yeah, what I was saying was the guy, you got 2.67 something meters per second.
Yes, sir.
Meters per second. So what you can do to get kilometers per hour is just multiply, is just convert back to kilometers per hour, or when you're doing your conservation of momentum equation, right, which is momentum before is equal to momentum after, you can just leave the units as they are, 20-ton and 10-ton truck. So you should get 30 tons times some V is equal to 20 times 14.4 plus 0, right? 10 plus 0. And then solve this, and V should be in kilometers per hour, right? Not converting. Okay, so you can get in kilometers per hour. Try it that way and tell me whether or not you get 9.6. Right? Okay.
Yes, sir.
Right. Good. And that allows you to get this answer. Of course, to find wait a minute. Yeah, of course, to find joules and whatever, you would do the right conversions, right? To find it in kilojoules. So you need to convert your tons out to kilograms, and maybe convert kilometers per hour to meters per second.
So I can
Right?
leave my answer in meters per second then.
Yeah, that's perfectly fine as well.
Sir, excuse me.
Yeah.
You could please, for this file drive question, right? Could please pull up the handout again, because I tried to look for it and I can't remember seeing in the example the using
Yeah,
potential
exactly.
energy inside.
Yeah, exactly. That's why it's a bit weird, because in other books, when you work a question like this, right? In other textbooks, if you can find another textbook with a question like this, they will add in potential energy, right? So what I did was I worked the question and noticed I didn't get the right answer. I got a little bit more. So I was like, okay, let me try it this way that I usually see in our textbooks. And I got the right answer. So I decided I'd show you guys this one, this way of working it, which gets this answer instead of the way that the example showed, right? But you can work it either way, right? It's just that there are other textbooks that does use this method. And if you think about it, gravity is acting on this body, right? So we need to factor in gravity as well.
This gives me like the CXC version topic than a tape version with left out certain thing.
Yeah, I think, let me see if I can maybe send you guys, I can't remember what I found this as. Yeah. I'll see if I can find another question that works in the same way and send it to you guys as reference, all right?
Yes, sir, it would be nice.
Yes, it's exactly that. It's like just like slightly more advanced version at considering gravity as well. Okay. But you can work it either way. I'm sure in if Miss brings it in the test, I don't know whether or not she'll bring it, but I'll mark either way. And if I don't mark it, they're right. Just send me a message. Neil, you said you would mark both of them as right, and then I'll check it over and give you your marks, right? So use whichever way you want. I won't penalize you for this because it's a bit unclear, right? as to which one you should use. Okay,
All right,
good.
thanks.
So is everyone else getting through this?
Yes, sir.
Anyone not getting these answers?
Excuse me, sir.
Hmm?
When this video will be uploaded to the to YouTube?
I'll try uploading it right after class, all right? It usually takes like a half an hour to, usually like when you end the meeting, Zoom starts converting the video or whatever. So it takes like a few minutes to process. And then it takes a while to upload on YouTube as well. So, you know, give me a couple hours, all right?
Okay, sir. Because I really need this.
All right, good. So is everyone getting this question number 6? Yes. Good. All right, so let's just move on to number 7, and you can go back to finishing number 6 on your own time, right? If it took you really long to finish number 6, please practice before the test, because Miss isn't going to give you that much time, right? Practice and get faster. Good, so number 7. A railway truck of 10 tons is moving at 10.8 kilometers per hour on a level track when it collides with a stationary truck of 2 tons, of mass 2 tons, and they move on together. Calculate the
So,
loss. Yeah.
just a quick thing. I'm getting 58,600 for the last question. So that the
58,600 joules or kilojoules?
joules.
All right, well, do I work this question, right? Because these 2 questions are the same, pretty similar, right? So if you see something you did differently than this question, then you know that that's where you made your mistake here, right? These questions are the same, so I'll work this one, and then you can look at the process, and then look back at what you did here and see whether or not you got the same thing. For common velocity, you got this, right?
Yes, sir.
Good. All right, so let's look at how we did KE for this.
I use
okay.
kilojoules.
Yeah, okay.
I use it in meters per second.
Yeah, no worries. Okay, let's see. All right, good. So a railway truck of 10 tons is moving at 10.8 kilometers per hour on a level track when it collides with a stationary truck of mass 2 tons, and they move together. Calculate the loss of kinetic energy due to the impact, right? And explain what happens to this lost energy. So we know kinetic energy before impact, right? One truck is moving and it collides with a stationary truck. So the kinetic energy comes from the moving truck alone. The moving truck has a mass of 10 tons and a velocity of 10.8 kilometers per hour. Of course, we need to convert this to meters per second. We multiply by 1,000 and divide by 3,600. That should give us a velocity of 3 meters per second. Right? Plugging that 3 meters per second with that 10 tons, right? 10 tons is 10,000 kilograms, right? Now, keep that in mind. Keep that 10 tons is 10,000 kilograms. Plug it into the formula just like that. Multiply it out, you should get your answer in kilojoules. The reason you're getting kilojoules is because we put in tons directly into the formula. Now, we can convert this to kilograms, putting 10,000 kilograms, and your answer will be in joules. And then you divide back by 1,000 to get it in kilojoules. All right, so that's half times 10,000 kilograms or 10 tons times 3 squared, which is 9. Half of 10 is 5. 5 nines are 45 kilojoules. All right. Okay. Now, kinetic energy after impact is based on common velocity, which is velocity after impact, right? We know how to find that. We do 10,000 kilograms, 10,000 kilograms times the velocity, which is 3 meters per second. Multiply this out, we'll get 30,000 kg meters per second. That is equal to the common velocity times the combined weight. The combined weight is 10 tons plus 2 tons. 2 tons is the stationary truck. 10 plus 2, 12, 12,000 kilograms, right, times V. Divide 30,000 by 12,000, we should get 2.5 meters per second. 2.5 meters per second. Using this 2.5 meters per second, we get the K after impact is equal to half.
Please explain that back again, sir. I ain't catch you so good.
Right? Remember, this is the same conservation of momentum, right? So momentum before is equal to momentum after. His momentum is conserved, right? So truck A collides with truck B, and then they stick together and they become truck A plus B, moving at some common velocity V. Before, it was truck A moving at some velocity V, which we know as 3 meters per second, which was given to us as 10.8 kilometers per hour. We multiply by 1,000, divide by 3,600, and we get 3 meters per second. So truck A, by some velocity V, A, which is equal to 3. Truck B is moving by some velocity VB, which is 0. So the weight of B times 0 is 0. The weight of A, which is 10 tons or 10,000 kilograms, times our velocity is 10,000 times 3, which is 30,000. Okay, so the momentum before is momentum of A before plus momentum of B after. The momentum after is the momentum of this combined body, which is the mass of A plus B times their common velocity V. So A plus B, 10 tons plus 2 tons, right? 10 plus 2 is 12,000 kilograms, right? 12 tons is 12,000 kilograms times its velocity V, which is unknown. Now we have our equation and we solve for V. V is equal to 2.5 meters per second. Make sense now? Yes? No?
Yes, sir.
The guy that was asking?
Yes, I understand. Understand. I get the 30,000, sir. Yeah, but the 12,000, right? Because when I do it, I have 1,200. So I never make a mistake at something.
1,200, no. 2 tons, 10 tons, right? 2 plus 10 is 12, right? 2 plus 10 is 12. 12 tons. 1 ton is equal to 1,000 kilograms. Therefore, 12 tons is equal to 12,000 kilograms. Then you multiply that by V. To get the momentum. Okay, good. Now, having established this equation, then consequently solving for V as 2.5 meters per second, we can find the kinetic energy after impact, which is of course half mv squared. That V is now 2.5 we use the mass is 12 tons, 10 plus 2. Now you can convert this 12 to 12,000 kilograms and get your answer in joules, or leave the tons and get your answer in kilojoules because we're already multiplying by 1,000. We're already dividing by 1,000 by not multiplying by 1,000, right? Good. So plug this into a calculator. Half of 12 is 6 times 2.5 squared should give you 37.5 kilojoules. Now the loss of kinetic energy is the difference of the two. Kinetic energy before, remember, at impact is 45 minus this 37.5 before, after. Subtract these two, your kinetic energy loss is 7.5 kilojoules. Okay, pretty simple. It's the same way we worked the questions before. Any questions on this?
So I understand how you did it. I think I did the same thing for the last question. You could
Well,
just do it.
let's work the last question. All right, the one I gave you guys to work, and see if we get the same answer. All right, good. But before we go back up to the previous question, any questions on this one before I go back up and work the other question? Any questions here on this and this? No? Yes? No? Okay, good. Continuing. Going back up. All right, let me just get something to write down. Okay, good. So a truck, 20 tons, moving at 14.4 kilometers per hour. It's a stationary truck, 10 tons, right? 0 kilometers per hour, right? Okay, move on, kind of calculate kinetic energy loss, common velocity. So common velocity, we just do 20 times 14.4 plus 0 is equal to some V. Of course, this V isn't going to be in kilometers per hour, right? Times 30, right? Tons, right? Keep everything in tons so that when you multiply out and divide, you should get the same thing. Let me just grab a calculator. And so we should end up with something like V is equal to 288 divided by 30, which is equal to 9.6. Okay. Which is equal to 9.6 kilometers per hour, or multiply this by 1,000, divide by 3,600, right? We get 2.666667.
I realized I went wrong. But it wasn't necessarily wrong. I didn't put as much decimal places for the velocity.
How much did you put? 3?
I just put 2.6.
You put 1.6?
No, sir.
No, well,
Sir.
let's see how much that affects the question. Yeah, go ahead.
Yes, sir. I want to know, like, if any one of those two answers correct, sir.
Yeah, either one's fine. Let's use
Okay,
2 decimal places and see if we get a decent answer, right? All right,
Yes,
good.
sir.
So this here, so kinetic energy before impact is of course based on this truck alone, right? So that should be before. Let's do before. Let's draw a line. So KE is equal to half M, the mass is 10 tons, right? 10. No, 20, right? 20, because the 20-ton truck is moving, times this, but in meters per second, right? So we got to convert 14.4 or times 1,000 divided by 3,600, which is 4. which is 4. All right. 4 squared. Yes, squared. So 20 times 4 times 4 divided by 2 should give you 160 kilojoules, because tons, right? Tons. Now this one here should be, as do after, KE, right, is equal to, let's just remove, let's write it back, right? 2.67 meters per second, right? After it's going to be half times 20 plus 10, which is 30, times 2.67 squared, which is equal to, and you plug that in, 30 times 2.67 divided by 2, which is 106.9335. Subtract the 2. You subtract these two, right? This one from this one, right? Subtract these two, you should get a difference of 53.0665, right? And the answer I have is 53.333. So you should still get a pretty close answer.
It was the
using
decimal places.
using 2 decimal places. If you use more, maybe the answer might be more accurate or less accurate.
I'd use 1.
Okay, good. All right. Yeah. Any other questions overall in general? Okay. All right, good. Well, if you don't have any questions, that's all I have for you. Good luck on the test Thursday. Is it Thursday or Friday? Right, good luck on that. Remember, practice, practice. All right. And you should be fine. Right. I'll find the other question that's similar to the pile from another source, and I'll send that to you as well with this handout. And I'll try changing the part where I said loss in KE to KE used or KE after impact. All right. Good. That's all I have for you guys. You guys can go.
Thank you, sir.
Good.